All right. Hello, everyone. Can you guys hear me on the back? Good. All right. So let's start our today discussion with example 11, which you're supposed to take a look. A bar is being pinned to point O, right? And the goal is to find the damping ratio or finding the equation of motion. Okay, so we know our standard form of the equation. The standard form is always mx double dot plus cx dot plus kx equal to 0. And we know that some parameters that we define, like natural frequency, k over m, and damping ratio, which is c over 2 square root of km. So we want to find out we want to find out sigma. In order to find sigma, we need c, k, and m. And again, I emphasize the c, k, and m are not this value, are not c, k, and the mass of this system, whatever it is. All right. We need to write the equations and figure out what are these coefficients, which we call them the system mass, the system damping, and the system stiffness. And again, the reason that I emphasize, because soon when we will get to the multiple degree of freedom system, these mass, stiffness, and damping, rather than just being one numbers, become a matrix. So it's better to get used to this idea. So like always, the first things, what is the kinematic of this system? It's obvious. You have a bar. It's being like joined at point O to the fixed wall. And without this damping and spring, it can swing. That's obvious. And now we put this damping and springs on this one. All right. So that's the motion. If this thing wants to move, we know that, where is my pen? Let's say if I disturb it, it's going to come down a little bit. Let's call this angle maybe theta, and this is the direction of motion. So that's the coordinate that we decide. Since it's a rotating system, it makes sense to use theta rather than x. And the direction is something that we decide. And based on that direction, we draw the free body diagram. So O, of course, is a joint. It only has these reactions. Damping always resists the motion, and stiffness the same. So if this point is O, then I can call this reaction OX and OY. Sometimes we need to find these reactions for the design purpose. And the force by the damping is the coefficient multiplied by the speed at that point, which is because of the small motion, I can assume it is A theta dot, right? Because the length is A and the speed of rotation is theta dot, so it is C A theta dot. And for the same for K, except for k, it is just a displacement, kb theta. That's my free body diagram. Since I have a rotating system, I can use the Euler formula. Since it's again fixed to a point, I can simply write down that sum of all the moment about that point must be equal to IO, the moment of inertia, the mass moment of inertia, multiplied by angular velocity, which is theta double dot. All right. So based on the positive direction that we decide, this is positive for us. And that's our initial decision that we said the clockwise should be positive. Now I can write down that I have C A squared theta dot, C A theta multiplied by the distance A. I have minus K B squared theta is equal to, for a bar with mass m, a slender bar, we know the mass moment of inertia is 1 over 3m b squared, right? The length is b. And this is, of course, theta double dot. I order these things, half of m b squared theta double dot plus ca squared theta dot k b squared theta is equal to 0. So that's my equation. I can even go further and simplify it more, or I can just leave it as it is. And now I can call this value the system mass. This is the damping coefficient. And this is the stiffness of the system. And simply I can find now the omega n if I'm interested, the natural frequency of this system, which will be 3k over m, right? Because b cancel out each other. I can find out zeta, the damping ratio, which is c divided by 2 square root of km, which k, I have k and I have m. I can just simplify them as k d4 m. So one more step, I can write down c, maybe, okay, it is 3, right? I have a 3 over here. 2 square root of 3, or 2 square root of 3 over there. Let's just do it in one shot. Km and a b squared. So that's my damping coefficient, right? So damping, which is Ca squared divided by 2km. Please check to make sure that I haven't missed anything. So I have Kb over here. I have 3 over there, which goes to the numerator. And yes, this is what we get. So that's our damping coefficient, damping ratio. And if I want the damping frequency, I just need to simply use this formula. 1 minus zeta squared. Right? Which last day we talked about the damping coefficient, the damping frequency, and the natural frequency omega n. So very simple and straightforward. You just need to get to this form of differential equation of motion. Okay. And now depends on these parameters. What is the value of C? What is the value of K and M and A and B, these distances? This system can be overdamped, it can be underdamped, or critically damped, which we discuss all of those scenarios. All right. So any question for this one? Seems simple, right? Agree? just give you a moment if you want to take notes, or if you just arrived late. Or let's just like this system. Let's just make a quick virtual prototype of it and see how it actually moves. I have a link. This link, let's say, because the question didn't give us any size. Yeah, maybe that's the size. Too wide. Just hoping if it works. So let's make the width of these things. Where's my keyboard? Okay, so 50. And the thickness 25. Oh. No keyboard. Shape. Right. So I have this link. Just random numbers for the length of that things. So it's I'm making a virtual prototype to see how that system is moving. So I have gravity. Obviously, if we build this system and let's just run a quick simulation of that, we know what will happen, right? Everything is finicky. And we don't have a keyboard. Oh. So obviously, if I run that one, it's just going to fall down, right? Nothing unusual. So let's pin these things to the ground or to the wall at this point. So I just built a joint at one end of that things. So this is a joint, right? Obviously, in this example, we just show a 2D, but in reality, it's a 3D. Right? Just seeing the 2D picture of that one. So our goal is to build this virtual prototype of that things, if we can be successful. Now let's run these things and see what will happen. So if I run a simulation for this virtual prototype that I built, so as we expect, it's going to swing left and right, right? Now let's add spring and dampen to it. So I have a spring somewhere here. Let's say this is a spring. I don't have damping. So no damping. 0. And let's stiffness Newton per millimeters. Let's go with 3. So I built the spring here, and let's change that color. I don't like that color. Oops. I should have brought my keyboard. All right, so we have a spring there, right? What else we have? We have a damping. Let's add a damping, maybe somewhere there. I don't want the spring, so no spring then. No spring here. And let's, for now, put a damping ratio of maybe a small values. Later we can change it. All right, so this is the system that we have, right? Very similar to what actually we have here. But this one, rather than just some, let's say, abstract equations, it is more like a virtual or what we have in reality, but it is virtual. Now let's run it and see what will happen. So because of the weight, it comes down and it vibrates a little bit. Let's give it some initial conditions as well. Initial condition. So as you can see, this link has a mass. It has moment of inertia, Ixx, Iyy, and Izz. But all we care in this 2D problem, right? It is Izz because we calculate the moment about point O, which is an axis coming out of the screen. So when I write down some of the M about point O, and I just write down IO here, it doesn't mean that there is not I, let's say, about other two axes. So this IO, it is in fact, it's about the axis Z, which is comes out of your screen or your paper, right? But since we are dealing with 3D problems, obviously in a 3D problems, we are going to have other moment of inertia as well. Let's see, this is a 3D problem. However, there is no motion about, let's say, x-axis and y-axis, so we just care about the z-axis. But all this information, the moment of inertia, they are there. So we want to give some initial conditions. Let's say because we are dealing with a rotating system, and maybe, okay, I need to figure out what are my axes. Oh, it's so small here. Cannot see it here when it's finished. Okay, one more time. So initial condition, velocity, local coordinate. I just put some random numbers. I'll explain you in a moment what actually is happening. With myself, I'm not quite sure. There's minus. All right. Now let's see what will happen if we run this simulation. Yeah. So I just give an initial kick to this system, like an initial omega or initial angular velocity, that 100 radian per second. That was I gave it. Now, if I let's say plot the motion of these things as we run it, because we don't want just a simulation. Then I will come back and explain what actually we are doing. Probably we wanted everything about z-axis. And it's doing some calculation. Too longer than I expected. This is where I need to pray that it doesn't crash. So what I'm trying to do here now, I'm trying to put, like, let's say, a sensor on these things. So when it moves, it measures for me the angular position of center of mass for this system. Okay, yeah, it happened. Now let's run everything and see how our model is gonna work when we run a simulation. Okay, so we give this initial kick, it moves ups and down, right? And as you can see, the amplitude of the vibration, it shows the theta, how the center of mass is moving ups and down. So the amplitude of vibration is become smaller and smaller. As we discussed last lecture, it's in a logarithmic way, the amplitude decrease. And the reason that it's not coming to zero, obviously because initially we have the mass for this system, and I didn't set that one to be the zero. I wanted the equilibrium to be where the mass is coming down. Right? So let's change the, let's change the damping ratio, maybe to something higher. So let's say instead of damping ratio of very small, if I set it to maybe just 0.1. Now let's run the system and see what will happen. So now we have a damping ratio which is 10 times higher than the previous one. So as you notice, it quickly returned back to the equilibrium position, right? Unlike the other one, which it takes some time to return back. And it stays there. Right? So like after 1, 2, 3, 4, 5 cycle, it returned back to its original position. And even we can increase the damping ratio to maybe even 10 times higher. I don't know what is the critical value for this system. We need to do some calculation. But if I run it now, or before I run it, I can just check my damping ratio, my natural frequency and everything. Yeah, probably with this font, you cannot see. But anyway, all the information are here. Now with a very high damping ratio, probably it's just going to quickly return back. Maybe I don't even need that much of time running the simulation. Maybe just 1 second will be enough. So obviously it is now critically damped, no vibration, right? It just moved up and it's flat. And again, the reason it's not coming back to zero because the place that I set my coordinate is not actually at the equilibrium. I could have set it, but I didn't want to take times for that. All right. So that's about it. And again, returning back to the idea of not critically damped, but some damping, which is the focus of our discussion. This is what will happen in an actual system. All right? If we solve those equations, this is what will happen in reality. We give an initial, let's say, condition to the system. It moves ups and down, and it flat out at the equilibrium position. All right. Any question for this one? And by the way, this software, toward the end of course, I will teach you how to use it. The reason that I leave it for that time, because if I show it to you now, then you don't like to solve the equations, right? Because it's seems to be easier, right? With no pain or anything, you just build the things virtually, and then let the computer to solve it for you. Now back to the boring equations. Okay, so the math, which is not that bad. At least it is good for, I guess, to make our brain sharper, hopefully. A few years ago, somebody came to me like for vibration, and he was in a business school, and I asked, okay, why are you taking? I didn't teach vibration at that time. This is my very first time teaching vibration here, but I taught it 250 times somewhere else. And he asked, oh, he was in business, and I asked him, why are you taking vibration? He said, because I want to become smarter. And I said, why? Because we've heard about the course that it has a lot of math and equations and figuring out how things are working. So apparently it's good for the brain. All right. So any question for this one or the simulation one? No? Good. Okay, you guys are quiet. I guess it might be the Zoom effect from last year. You are the generation that were 1 year. You were just sitting in Zoom classes. But please feel free to ask questions or don't be shy anyway. So let's then move to example 12 and quickly solve example 12. A mass, pulley, a spring, the system is obvious, it moves ups and down. We simplify the question by saying that the pulley doesn't have any mass, but we will solve problems when pulleys has mass. It's not really that complicated and closer to the reality. Soon, we will see one, I guess, in your tutorial, maybe not today tutorial, but in future tutorial. And also no friction, but also we will add friction as well to the system. But for now, we stick with no friction in the pulley and neglecting the mass of the pulley. So then we know how this system is working. We need to make a decision, and we assume that this is the equilibrium position, and we need to make a decision for our coordinate. Let's say that I decide X to be my coordinate, and I decide that coming down is positive. Again, it's totally up to me. I can show it upward, and it doesn't matter. The result will be exactly the same. So this is the equilibrium, a fixed point. And at this equilibrium, I decided that initially my system, I move it down, and this is the X coordinate that I selected. Now I draw my free body diagram based on this decision. So if the mass is moving down, let's say this is the mass, and obviously that pulley is coming down with that. So let's draw the free body diagram of the pulley over here. So the forces, the damping always apply a force, the opposite of the motion. So that's the force for damping, and it is the coefficient multiplied by the velocity, Cx dot. It's easy. Between the damping and the pulley, I'm not sure what's going on. So for now, I just put a force. I call that force maybe F. Or it should be the opposite way, right? Let's first draw it for the pulley. So because we are bringing the system down, I have a reaction in the middle. Let's say that's point O. Yeah, maybe it is easier to draw it that way. All right, let's call that force F. We don't know what is that value. And for the pulley, obviously, we have a tension here. Let's call that one T. The same tension goes to the other side because there is no friction. So this one also is T, right? If it is T, this one also is T. But how much is this T depends on the stiffness of the spring. If I move down this mass by X, I can realize that, let's say, if I draw a line here and I exaggerate it, if the center is moving by X, right, if this distance is X, just let me zoom a little bit so you guys could see. If from O to O prime, it is X, then obviously this point is going to be 2X, right? You guys can see, I guess. So move back there. Therefore, I can claim this T is equal to 2kx, right? Do you agree? Or it is k multiplied by 2x if you want to like. be really picky. Okay, stiffness multiplied by 2x. So since this pulley doesn't have any mass, I can write down that sum of the force, like this equation, ma, but I don't have any mass. This one is 0. Therefore, 2t must be equal to f, all right? And from here, I managed to find f for kx. So we solve one side of these things. So this action and reaction over here, this is also f. And this f we managed to find is equal to 4kx. So we have our free body diagrams. The rest should be easy. Sum of the force is equal to mx double dot. And we know the positive direction. This is what we decided to be the positive direction. Again, as I said at the beginning, it doesn't matter if you show your positive direction at the beginning, upside down or opposite direction, but you need to follow that direction. So for you, this is the positive direction. If somebody draw the free body diagram, but upward should be the positive, you would get the same result. So what do I have? I have minus cx dot, I have minus 4kx equal to mx double dot. So my equation now, mx double dot, cx dot plus kx, 4kx is equal to 0. And again, our standard equations, except that our mass is m, coefficient, damping coefficient c, and the stiffness is 4k. Right? And we can find out whatever the question asks, which for this system, it is just the equation of motion. But if we are looking, let's say, to find the frequency of vibration for this system, it is omega d because it has damping, right? And it's not omega n. Omega d, we know it is omega n 1 minus zeta squared. Omega n, we know how to calculate it. It is k, stiffness over m, and zeta, we know it is simply c over 2km. Which it gives me c over 4km. Because remember, a stiffness is 4k. The stiffness that we need to put in these equations. The formula are always the same, the formulas that we use. It is just this value of m and k and c that can be different. All right. So that's an example for pulleys. We can similarly make like the virtual model here, which I'm not going to do it now because there is no point. Later you will learn and you can do it yourself. It's not that of interesting system, right? Any question for this one? No, we're good. All right. Then I'll just give you a moment if you want taking notes. No notes. Okay. Then let's solve the example 13, which it looks like a little bit more complicated, but in fact it is not. So I give you a moment to just read the question, try to see how you can approach it. You were supposed to do it before, but spend a minute and read it. So then we'll solve it together. Oh, you want the last one? Okay. Go ahead. So from the number of people in the class, I can guess probably there are some midterms going on, maybe. Or maybe it was just because of rain. You guys didn't feel coming to the class? Those, sorry? It's Friday. It's Friday. Yes. But Fridays are always better, right? Because you have hope for the weekend. All right, so if you're done, let's now take a look at this question. So what do we have here? We have a wheel. Apparently, this wheel and hub, maybe I can guess it's a model for maybe a train because they have some sort of similar system. But for now, we just look at the problems conceptually. So we have this wheel and hub attached together. And the it says the radius of gyration is k is 20 centimeter. So we talk about the radius of gyration in lecture 1 or 2, I can't remember. And sometimes question it shows it by k, capital K. Do not confuse it with a stiffness. When we solve problems, obviously we need I, and it says about point O, or the center of mass, it is KO. It is mass multiplied by KO squared. All right. So always we need in our calculation, we need moment of inertia, but sometimes just for easiness, people use the radius of gyration. So the mass of these things is how much is 2 kilograms, and we better be careful with the units. The radius of gyration in meter will be 0.2 squared. So this is IO if I needed the mass moment of inertia about the center of gravity. So what else? The question says that the radius R is 20 centimeter. So that's one piece of information. And also the stiffness, we have the stiffness and we have the damping ratio. All right. And the unit seems to be in the right order. We want to find out the damping coefficient. No, what do we want to do? We want to calculate the damping ratio. So we need the equation of motion. Okay. And also it says that assume that the cylinder rolls without any slipping on the hub. So this point is roll, no slippage, right? So when we see that note, there is no sliding, it is no slipping or slippage. It means that we can assume for a moment this wheel or this hub are rotating about that point. Let's call that point, point maybe A. And we call it center of rotation, which you should be familiar from dynamics or machine dynamics. So anyway, whenever we have a disk, we have a roll, we have a wheel, and the question specifically says that it's rolling without any slippage, then for a moment you can assume that the whole thing is rotating about that point of contact. So I assume the rotation theta, then based on that assumption, I can figure out the stiffness force. Let's make it bigger. So I can assume this is the stiffness force, which will be K or theta, and this will be the damping. Right? Remember the damping, always the opposite of the speed. So point O try to goes to the right, and the force by the damping will be C R theta dot. Okay, so Now that I have my free body diagram, I can write down sum of the moment about point A is equal to IA theta double dot, right? The Euler law. And what about point A? Point A, the point that there is contact, there are two forces which we don't know their value. One, let's call it N, right? And the other one, let's call it maybe AX or whatever we like to call it, F. We don't know the value for those. That's why we are taking moment about point A to get rid of them. So doing that, I will have minus K R squared theta C R squared theta dot equal to, I need IA. So we know how to find IA. It is IO. We need to transform the mass moment of inertia. M R squared, and this is theta double dot. If I organize everything, IO plus M R squared theta double dot C R squared theta dot and K R squared theta will be equal to 0. Now this is my mass. This is my damping. And this is the stiffness. All right. So the question asks for the damping ratio. Damping ratio simply is C over 2 square root of Km. So it will be then CR squared to what is K is KR squared multiplied by M, which M now has a different form. It is IO plus MR squared. Which you can just substitute these values and find out what is the value of the zeta. And obviously, if zeta is less than 1, is one story. If it is bigger than 1, that's another story, which you know, right? It's underdamped or overdamped. Right? So, and similarly, if you need the natural frequency of this system, omega n, you know how to calculate it. If you like to know what is the damping frequency of the system, you know how to find it. Right. Question? Yes, please. Oh, the Lagrange equation. Yeah. Okay, so this one has damping, right? Remember, for damping, you need to calculate R as well. R is half of C. Who remembers? V squared. We agree? All right. So you have then your V, which is R theta dot. Then what else you need to find out? You need to know the kinetic energy, T. Kinetic energy for a system that is rotating. Again, if you remember, half of IA theta dot squared, right? Which you already know what is IA. IA is IO plus MR squared. And we have T, what else we need? We need U. the potential energy. So the potential energy here, mass is out of the question because the gravity doesn't do anything for the vibration of this system. It is just a spring, half of K, and the deformation, which is R theta squared. So far good. So 3 parameters, R, T, and U. Now, all we need to do is taking derivatives. What is the Euler formula? The general formula, d over dt, derivative of t with respect to theta dot. This is our variable here. Derivative of t with respect to theta dot. And then we have derivative of u with respect to theta minus derivative of t with respect to theta. What else? Derivative of r with respect to theta dot equal to any external force. External force. All right, which here, remember, the external force has to be a moment because we are dealing with a rotation system. Okay, when we are dealing with a rotation system, instead of a force, it has to be an external moment, like a couple applying on this system, which is we don't have anything for now, and this part obviously is 0. And I just leave the derivative to you. I guess it should be easy to take the adjustment.
You always have to solve it in per I.
You have to always take the derivative about a point, okay, that there are some, let's say, external force that you don't know what they are. Okay, so the reason that I'm taking the derivative about point A, because I wanted to get rid of these N and F, correct? And whatever we take the derivative, whatever we take the moment, sorry, I said derivative, wherever we take the moment, like some of these moment about point A, that moment of inertia has to be about that point, and that's the Euler law. All right, so it was a good question from you. So here is the Lagrange approach as well, or Lagrange method. And please just take the derivative. You should get the same equation. If not, it means something is not right. And have a good weekend. See you on Monday. And by the way, if you don't pick your paper, exam paper, my office is open. Most of you did. I assume that you don't need your exam paper, and I will share them on Monday. Thank you. So, just give me a second. Oh, not working. Maybe. Okay, sorry. Go ahead.
So here we consider the net energy, but we only consider the rotation energy. Are we considering the translation energy?
You are considering the whole thing. Wait outside for me. I need to explain that to you.
Hi, good morning.
Good morning. How are you?
Hi. today's ring is so cold.
Tired? Why tired?
Yeah, we work on a 426.
426?
It's about
Can you answer?
mechanics. Yeah, chef designing something.
Oh, yeah, yeah. Okay.
Do I have to pick up my midterm? Is it necessary?
No. I said if you don't, it means that you're okay. If you don't do it, and I just right?
Yeah, I already did the midterm.
That's what I like. But some students they like to have. Nope.
Can you help me close the second question so I can do it?
What is the second question?
The one with the
What is it?
yeah, for this midterm.
I posted the solution. Yeah.
Oh, okay.
Yeah. Right.
Do it again.
5 minutes.
Yeah, so I
After
really
the-
don't need the paper.
Okay, then you're good.
Are you actually going to shred it or are you just going to throw it?
Sorry?
Are you actually going to shred the midterm or are you going to throw it away?
I throw them.
Oh, okay. I'll probably want to shred it myself.
Okay, so then just go there and pick it. Let me just grab this. Let's go outside. This computer doesn't want to. Stop the Zoom. Probably I will stop recording as of next lecture.
Oh, really?
Yeah, I realized like not too many are using them, except maybe you. And, or maybe I need to think about it. Okay.
I thought it was a policy for it because of
What?
we're still in the middle of the pandemic. So
I guess there is no requirement. But yeah, but maybe I'll do. Sorry?
no, I thought you are talking about maybe 465.
No. So let me just answer your question. Okay. So remember, go to the lecture and then I give the review of the Euler law and the kinetic energy. So we said we have 3 scenarios, right?
Yeah, so
Okay, so right? So we said we have 3 scenarios. Yeah. One is only moving, one is only rotating, and one is doing both.
yeah,
Okay. So remember here, we said for this is doing both.
yeah. But did you pick
It's doing the rotation and the translation. So we need to use this one.
Yeah.
But we proved that at the end, we end up with these things, and that thing is actually is IC.
Oh, okay. I
You
see.
see what happened?
Yeah.
That's all. So
So basically they are equal, right?
they are basically equal.
Okay.
In fact, you are considering both of them,
Yeah.
right?
Oh yeah, that's so because I was thinking it's rotating and
It's also rotating and translating, but
but we can express in this term.
exactly.
Okay.
Makes sense?
Yeah, that makes sense.
All right.
I just forget about this.
Okay, now my